Okay. So, we have said the cross correlation is one of the methods for enhance the result of autocorrelation technique. The other method is called central clipping. If I have the speech signal like this, I want only the central part, because if you see the F0, I want F0 is, or you can say the filtering also, clipping, and that F0 is up to 500 Hz is sufficient. Okay. So, I do the central clipping in the signal, and all the high amplitude variation can be avoided, because high amplitude variation give me the autocorrelation function is long variation. So, instead of taking the high amplitude variation signal, I can clip the signal in central part, and that signal can be used to find out the autocorrelation and calculating the F0. Okay. So, this the algorithm is very simple. So, clipping, how do we find out the CL? Generally, it is CL equal to 1/4 of the peak. So, how do you do that? Suppose I have taken a 20 millisecond window signal. So, within the 20 millisecond, I can find out the maximum peak. So, let us 20 millisecond signal is represented by xn. So, if I find out the maximum amplitude within the 20 millisecond, then I can say the k into that max amplitude will give me the CL value. Okay. K value is between 0.6 to 0.8. Okay. Now, if I want that I have a signal which is lot of variation in amplitude. So, instead of taking the single max, I can divide this 20 millisecond signal in maybe another 4 segment, maybe 5 millisecond, 5 millisecond, 5 millisecond, 5 millisecond, and from each segment find out the maxima and take the mean of that maxima to find out the CL value. That is the formula. Okay. So, this is called central clipping to improve the autocorrelation based F0 extraction. Another procedure, instead of taking the signal, if you remember in LPC analysis that if this is my vocal tract transfer function Hn, and if I apply AUN, then I get speech signal Sn. Now, if you remember that linear prediction, what I want to predict signal Sn and if I subtract the predicted signal, so the remaining is nothing but a AUN, which is nothing but AN. Error signal is nothing but a excitation signal, inverse filtering. I can say that I have designed 1 by Hn and I pass the signal Sn, I get AUN, which is the error, LPC prediction error. Okay. Now, if you remember, the F0 is part of the excitation, not the vocal tract. So, F0 information is here, not in here. So, I can extract the F0 from En signal. So, instead of using Sn speech signal which has a lot of variation which is introduced by Hn. Okay. So, instead of take the Sn, I can pass the Sn to a inverse filter to get the AUN, which is the error signal of the LPC analysis. From the LPC error signal, I can find out the F0 value using autocorrelation. Is okay? Next, that not very efficient or high fundamental frequency convolution is very expensive process, that some pros and cons of autocorrelation technique. So, computation efficiency can be improved if I use the FFT algorithm to implement that correlation, the calculation of the correlation function. Okay. So, this you can read it. Now, instead of autocorrelation, since autocorrelation is required, the sample is multiplied by the sample. So, if it is a, if you see if it is a 16-bit signal, 16-bit multiply by another 16-bit sample. See, worst case, it requires a lot of memory, and also multiplication is computationally complex. So, for hardware implementation, or when that computation facility is not that enough, you can use average magnitude difference function, which is called AMDF, average magnitude difference function. Average magnitude difference function. So, what is the theory behind it? What is the methods in here? So, suppose you have a signal xn which may have a period, which has a period, which is a periodic signal, some fundamental frequency is there. Now, if I want to plot x0 versus x1, then x0 versus x2, x0 versus x3, and that way. So, x0 versus x0 will become here, x0 versus x1 some come here. So, I can get a scatter plot if this sample is exactly matched with another sample, let us xk, then I get a point in here, x0 is equal to xk, then I can get a point in here, then I can get a point in here. So, along the 45-degree line, all x0 which is matched with xk will be like. Since which is not a, you can say it is not a exactly periodic signal, then what is? So, instead of calculating the exactly 45-degree line, what I want to calculate the deviation from the 45-degree line and find out the average value of the deviation for each delay. Then plot that average deviation value against the delay. So, what is the function? 1 by n equal to 0 to n minus k, xk minus x of n plus k. So, for all the sample, I am dxk. So, k equal to 0. So, it is 0 minus, so x0 minus x0, x0 minus x1, x0 minus x2, x0 minus x3. So, for all deviation, I am finding out the deviation and add them and find out the average value of the deviation. Then next I calculate k equal to 1. So, shift the x0, instead of x0 I put x1, I put x2, I put x3. So, all deviation, average deviation will be there. Okay. So, deviation will be minima when it matched with the period. So, if I plot the deviation plot will look like this. So, minimum deviation will be happen at the period or at the f0. So, this is f0, this is twice f0, this is thrice f0. Okay. So, this technique is used to find out the fundamental frequency when the computation power is less. But what is the drawback? Less computational complex is okay, implement hardware. The performance is poor and it does not cater for variation in energy of the speech signal. If you see, the deviation depends on the variation of the energy. So, suppose this time I speak some speech which is less energy and next time is high energy, the deviation will change. Or I can, if I say, suppose there is a long vocalic region, the amplitude has energy has changing, then there will be a variation will f0 will occur here also. So, that kind of energy, so amplitude problem is there. Okay. So, autocorrelation is highly used and this is used when I can say I require a average rough estimation of f0 is sufficient, but computational complexity will be very less. In that time I use AMDF, average magnitude difference. Okay. There is other algorithm also, from maximum detection, some magnitude difference. So all other methods are also adaptive filtering, circular average magnitude difference function, cumulative mean normalized difference function. So all other methods also available. Then frequency domain PDA, pitch detection algorithm, or F0 detection algorithm. Frequency domain PDA operates on speech spectrum. So distance between the harmonics is the fundamental frequency or inverse of the speech period. So what is the key philosophy behind the frequency domain PDA? That if a signal consists F0, then harmonics will be repeated F0, twice F0, 3 F0, 4 F0. Okay. So from there I can calculate the F0. So main drawback of the frequency domain PDA is the high computational complexity. Any signal to transform in frequency domain is a computationally complex. Okay. Now there are two kinds of PDA are mostly used: harmonic peak detection and spectrum similarity. So detect all the harmonic peaks. So suppose I have a F0, this is my spectrum. This kind of spectrum is there. So if you see, if this is F0, this is twice F0. All harmonics are repeated thrice F0. So from there I can find, okay, if this is 2 F0, so I can find out the repetition distance, and that give me the F0 value. So how do you do that? It's called Coombe filtering. If you remember, the Coombe has a peak and gap. So if I say this is F0 beginning, twice F0, 3 F0, 4 F0, then I can find out the average difference between this gap, rough average difference, that give me the average value of the F0. That is the idea. Okay. Spectral similarity, I have a spectrum, I can simulate this is my F0, this is twice F0, this is thrice F0, and try to find out the correlation, I mean whether it is matches with the original spectra or not. Once it is matches, you said, okay, this is my F0. Spectral similarity based F0 detection. There is a time frequency domain F0 detection also, lot of algorithm on time frequency based F0 detection. But if you see, most of the time today, recently this state is a software which is available in free and open source, by which you can extract the F0 reliably. There is other software also. If you can use the PRAT also. PRAT also you can export the F0. They PRAT use the autocorrelation based technique to extract the F0. So using PRAT also you can extract the F0 value. Okay. So this is the F0 extraction, you can say. So now if I give you a speech signal, you can extract the F0 and you can plot the F0 against the time. So for every 10 millisecond, if I got a F0 value, I can plot it to find out the F0 contour. During the prosody modeling, I will discuss lot about F0 contouring, and if you see how this F0 contour is useful to model the prosody, even if F0 contour can be useful in ASR also. I will show you that things in lecture number 8, week 8. Week 8, prosody modeling will be week 8, and the speech application will be the next week, this week 7. Okay? Thank you.